I guess we'll start. So we have Iordanis, Kerenidis, quantum methods for optimization and machine learning.
Thanks, Michael. Thanks to the organizers for inviting me here. I will be talking about some work that I have been doing for the last couple of years. There will be some things which are from a year or two ago, some things that we just finished last month, and some things which are not finished yet. So there will be a little bit of everything. So I guess what I have been trying to understand the last couple of years is kind of try to ask a very simple question. Well, it's simple to pose the question, but not very simple to answer the question, which is, what will be the applications of quantum computers, right? So obviously we can say that let's build them first and then we'll figure out what to do with them. So I'm very happy with that answer. But I want to understand at least where should we be looking to find these applications, right? So we had talks about quantum chemistry, about simulation of many-body physics. But since I have no idea about chemistry and no idea about many-body physics, I will look at something that I might have some better success in looking at, which is optimization in machine learning. Okay? All right. So I guess the result that kind of jump-started this area, I'm sure there were results also before that, but the one that kind of made people more interested in this was the result by Harrow, Hasidim, and Lloyd from 2009, which is the famous HHL algorithm. Okay? So there are quite a few ways of stating this algorithm. One way is to say that quantum computers can solve systems of linear equations. Then obviously you will have Scott to say that you have to read the fine print. Here I made it in red, not fine, but there are many kind of things that you have to be careful when you say that we know how to solve systems of linear equations. The first thing is to say that the solution that you get from the quantum algorithm is not the solution to the linear system. It's a quantum state that corresponds to the classical solution. It gives you a vector that corresponds to the classical solution. The second thing you need to understand is that this algorithm could be exponentially faster in some cases, but actually the running time is kind of a complicated thing that you need to really understand how it works for your specific problem. And the third one is that you do have to assume that you have some sort of quantum access to your data. Okay? So there are many different ways of saying what kind of quantum access you need. So we will see a little bit more, but I think Stacy also discussed this yesterday about different types of quantum access to your data. Okay? So the good thing is that there was a lot of excitement about this result. The excitement, to be honest, came more from not necessarily from the people who are in academia, but people who are in big companies. So I'm just citing here something from a quantum machine learning workshop during the NIPS 2015 that was organized by Google and Microsoft. And they wrote that it opens the possibility of dramatic speedups for machine learning tasks, richer models for data sets, and more natural settings for learning and inference. So that was a few years ago. So I really tried to understand what are these dramatic speedups and where can we actually see these things. I do want to make one small point for the more complexity theory people is that basically this problem, like solving the systems of linear equation, is a BQP complete problem in some sense. So kind of you can see that this is what quantum computers can actually do, right? I don't remember. Anyone remembers under what reductions you can get the BQP completeness?
Standard carbon.
Yeah, it's relatively
I think it's straightforward. Yeah. Yeah.
I mean, you might lose a lot in the reduction in terms of efficiency.
Kind of. Yeah.
Right, like there may be a big blow up in the reduction.
Yeah. All right. So I want to start with a few remarks about quantum machine learning. Somehow, I don't necessarily feel that you should all agree with them, but at least this is how I see things, okay? So to me, if you want to really get some exponential savings in this area, you will need a quantum computer, which is like a big quantum computer, and you will need to have some quantum access to your data, okay? So your quantum access could be because your data is really quantum. Yeah? I said that not everyone will agree, so yes.
So that is true if you want to get an exponential speedup in the fashion that HHL is looking at.
Yeah.
But if you're looking at, say, a manifestly quantum model that is making predictions, it's possible for you to have an exponential speedup over simulating that because implementation of the quantum model could be complete. So it depends on the input and the output. Or sorry, for the input, for some problems it depends on the input. Yes, you're absolutely right. But if the prediction is hard, then
yes. So let me say that I'm trying to look at problems that people are already kind of interested to solve. Like I'm sure you can come up with things that you can do exponentially faster without having what I claim here. So I agree with you. But for the things that I will discuss and the subset of quantum machine learning that I'm more interested in, I don't know how to get exponential savings somehow if you don't have some sort of quantum access to your data, right? Okay, the second thing is that I kind of find it that it's kind of the most overhyped and underestimated area of quantum information at this point. So obviously this is a contradiction, but it's not a contradiction because it's a disjoint set of people who overhype it and disjoint set of people who underestimate it. So both can happen at the same time somehow.
It should be overhyped, right?
Sorry?
You read your sentence, it means that the overhype is underhyped, right?
Oh. Now let's over-underhype it. So that's my goal. No, but really what I need to understand is, there are people who say that, oh, you can do everything. There were other people who say that you can do nothing. So what I'm trying to understand is basically where we are in the scale of, hype and, nothing is possible, kind of.
And where are you in this?
So ask me again at the end of the talk. Maybe you'll get a better feeling of where I am, or then we can discuss it, right? Somewhere in between. Okay. Having said that, I still think that it's one of the most convincing reasons that I can find, at least for myself, to actually say that, yes, we should really spend all this effort and time to actually try to build quantum computers, like big-scale quantum computers, right? I'm sure there are other reasons to do that, but for me, being able to solve optimization problems that everyone kind of tries to solve in practice, or machine learning tasks that people actually really want to solve, and they're getting to the limits of the HPC capacities, it will be a good thing. So to me, this makes it the whole effort of building quantum computers quite an interesting one. Okay, so very briefly, what basically Stacy also explained yesterday. So I guess every time you want to have some sort of quantum machine learning, or at least the type that I'm looking at, there are kind of two steps. The first step is that there is this data that kind of appears, or somehow you make some experiment, you get this data. You have to do something with your data. Like the simplest thing is that you can store it classically. So somehow you need to spend time linear on the size of the data to actually even see the data and write it down, right? So when we want to say that you have quantum access to the data, I want to assume the following, that I allow you to use some sort of data structure, which could be something a little bit more elaborate than just writing the data one after the other. So you can use some sort of array or tree structure or something like that. But I don't want to basically pre-compute everything and then try to tell you that I can do good things because I spend all my time doing the pre-processing, right? So I want to be able to store, to update, and to delete any element of this data in polylogarithmic time, okay? And then what I call quantum access to this data is basically being able to do quantum queries in superposition. This is exactly what you need for all kind of query algorithms. How easy or difficult this is to do? Well, it kind of depends. It could be that Aij is a very simple function of I, j. You have a very simple circuit to actually do it, so sometimes it's very easy. Sometimes it's less easy, so then you have to work more, okay? And also there are many other models. There's the sparse model, there are more models. And then the second step of this is that once you have pre-processed your data and you have your data there, you need to do some computation to this data. For example, you need to learn some property of this data, right? So it's on this step that the running time of the quantum algorithm can be actually more efficient than the classical one, right? Somehow, we are not saving anything here. In fact, we are just saying that only you can at most spend polylogarithmic time more, right? But somehow it's here that we want to have an advantage, right? For example, classically, you might try to do some computation that is like cubic on the dimension of your data. Here, you would like something which runs much better than cubic on the dimension of the data. Okay? All right, good. Okay, so I will give a very briefly explanation about the first example that we tried to come up with. So the idea was, can we get some example of something that people actually really want to solve and figure out a quantum algorithm that I can prove something about the complexity of this algorithm, okay? So I guess this problem is the Netflix challenge or the recommendation systems. The problem is very simple. I give you a matrix of users and products. You have some knowledge about this matrix because some user bought some product and they said thumbs up or thumbs down, okay? So you have some elements of this matrix. You have a lot of question marks about this matrix because you don't know if this user will like this product or not, okay? The whole point is to figure out where are these good products for the user. Like a user comes into the system, you need to be able to recommend a good product, right? Okay, so I guess it's an application that Netflix or Amazon want to solve, maybe not us, but anyways. So there is a very clear mathematical problem that comes out of this, which is what it was called matrix reconstruction. So basically, what is the main way that we knew how to do this classically is to say that, okay, I'm going to take this matrix, and somehow I'll find a way to reconstruct all the missing elements of this matrix in a way that this reconstructed matrix should be close to the real matrix that I don't know, right? And then what will I do? Well, if this user comes into the system, I will look at this line, I will figure out where are the high valued elements, and I'm going to recommend an element like that, right? So the first thing we had to do is to realize that the matrix reconstruction is not really what you want to do. It's kind of overkill in the sense that if you want to find a high element on the matrix, you don't necessarily have to reconstruct the entire matrix, right? Because reconstructing the entire matrix will obviously take time, which is linear on the size of this matrix, because at least you have to write it down, right? So the first thing to notice is that if you manage to sample from this matrix, it's good enough in the sense that you're going to sample high-valued elements, like the ones of the matrix, right? So this was the first thing that we had to do, kind of change a bit the problem that we were trying to solve. The second step was to kind of reduce this problem into some sort of linear algebra procedure. And this was kind of basically had to do with estimating the singular values of this matrix. And then we can use the algorithms that can show that you can have quantum algorithms for doing the singular value estimation, which could be exponentially faster sometimes. So we also had to show that whether this time, this specific thing here, you can actually have exponentially faster algorithms or not, right? So, So basically, using this fact, we could show that quantum computers could provide competitive recommendation systems exponentially faster than non-classical algorithms. So what did we have to do for this? Well, first of all, we had to improve the linear algebra that we knew so far, because we knew how to do linear algebra like matrix inversion or matrix multiplication for sparse matrices. This is what the HHL and the other algorithms could do. What we needed to do is not for sparse matrices, but also for low-rank matrices. Why low-rank matrices? Because the assumption that you have in the recommendation systems is that basically this matrix is well approximated by a low-rank matrix. Okay? So we had to first figure out ways of doing this kind of linear algebraic commutations efficiently for low-rank matrices. Okay? And the running time that we got is something which is polylogarithmic on the dimension of the matrix, which is good. And then, as you know, there are some factors in front of that where the running time of the algorithm depends polynomially. So if these factors are very big, for example, if it is like the dimension, then you are not really doing something, right? So for example, if this factor was the sparsity of the matrix, then the sparsity of this matrix is actually very big. It's like the dimension, so you wouldn't get an exponential speed up. But since we managed to get this kind of procedures for low-rank matrices, what we managed to put here is actually the rank of the matrix. And the assumption is that the rank of the matrix is much smaller than the dimension of the matrix. And this is not our assumption. This is the assumption of classical recommendation systems. Okay? Okay, good. So this was just one example. In theory, this algorithm works. In practice, I have no idea if it's going to work. Like, I really don't know what kind of accuracy, how well your recommendations are going to be, or really what kind of running time you will have in practice. I also don't have data to try to understand if this actually runs well or not. So if there are people from Facebook or the Chinese Facebook or Amazon or the Chinese Amazon and they want to give me data, I'm very happy to try and see if this actually works. Okay, So then we try to look at something else because we solved a very specific problem. The question that we had is that can we get some sort of general methods that you can use in machine learning or optimization? So what is kind of the method 101 that you people use in order to do optimization? Is kind of gradient descent. Okay, so what is the whole point of gradient descent? You kind of guess a solution. You kind of look around to see what is the best way to proceed. You kind of take that a step, you go to a next solution, you check if it is a good solution or not. If not, you find a direction that it's good for you to go that way. You continue until you end up somewhere where it's kind of a local minimum. You're around there, you output this. Okay? So okay, it's a very high level explanation, but this is kind of what iterative methods do. You start with an initial solution, you figure out how to update your solution. After a few steps, you have to prove that you converge to something which is very close to a good point, right? Okay, so the first order is called gradient descent. The second order are called interior point methods. So what we managed to do for that is we managed to have some sort of quantum version of gradient descent, but it only works for the case where the gradient is actually a simple function to compute, meaning that it's a linear function. Okay? So the only thing we can solve is a gradient descent where at every step, basically you're solving a linear system. Okay? So now you can say that if what I do at every step, I solve a linear system, then basically you can write down your entire problem as a bigger linear system, and you can use HHL or whatever algorithm you want to solve your linear system altogether. So you don't really have to do gradient descent if you're basically having a linear gradient. But somehow in practice it's much better for you to do this gradient descent even if you're having linear updates than actually try to solve a very big linear system. And I'll tell you why. The first one, okay, sorry, I'll tell you about this. But the reason is, for example, if I want to do a linear system in a very big matrix, I would have to have some quantum access to this very big matrix, right? If I'm trying to solve the same linear system, but with some sort of gradient descent, or better with this stochastic gradient descent, what people do in practice is that they don't look at the entire matrix at once. They just chop the matrix into small batches, and they solve linear systems on this smaller dimensional matrix. Which means that at every time I want to use my QRAM, I only have to quantumly have access to a much smaller matrix than the entire matrix. So it depends on how, so the idea is that usually, okay, in many cases your matrix is like this. Because you have many points, this is the number of points, and these are like the dimension of your points. So in cases where something is like this, what you do is that instead of solving the entire linear system once, you just cut the thing like this, and you solve linear systems, you update, you do the same, right? Now, how small this is, there are cases where basically you do it line by line, okay? The idea is that you don't have to go all the way down, because you have too many points that live in small dimension. You don't have to see your entire matrix.
Eventually, won't you have loaded the whole thing?
No.
But wouldn't it be
You don't have to.
one-shot thing that loads whatever you have loaded, and that would do just as well?
No, say it again.
At some point, you're doing gradient descent, right? So at
Yes.
each step, to estimate your gradient, you're loading like a small part of the matrix.
Yes.
So by the time you end, you'll have loaded some amount, right?
Yes, but you can load it one after the other. You see what I mean? Like my question is, how big is my superposition that I need? How big a quantum query in superposition do I have to make, like at every point? And at every point, you need to have a superposition of these points. Then you see what I mean? So you don't have to have a coherent superposition of all these points, which means that your QRAM would be 10 to the, 12. You can split it into smaller chunks and have, it's much easier to have 1,000 QRAMs of 1,000 qubits than one QRAM of 1,000,000 qubits. Because it's much easier because it.
You have no idea how this thing is ever going to be built anyways, right? So.
But you do know how deep, you do know that the state on 6 qubits is much easier than a state on 100 qubits somehow, right? Okay, sure. So in my opinion, I think it's easier, but maybe it's not. You're right. Okay? But, all right, cool. The other thing that we had to do for this paper is actually further improve these linear algebra procedures So now they don't only work for low rank matrices, but they also work for other type of matrices that you get some different kind of guarantee on the running time. Okay? All right, so I was kind of very impressed with Robin's talk yesterday of how clean everything was. So I tried to have one slide where I try to explain, maybe in my way, on how to do quantum linear algebra somehow. Okay, so this is the one slide that kind of, basically, here are some things that you may want to do. You have a matrix A and a vector X. You want to output some sort of operation on these two things, like you want to output A times X or A minus 1 times X, or you might want to project X onto the top eigenspace of this matrix, or some sort of operation that basically has to do with the singular values of this matrix, right? So how do we do that? So the first step is that we have to figure out a way to map this matrix A into some unitary U. Okay, this is what you can call block encoding or have a QRAM efficient implementation. You somehow map this A to this U so that somehow the spectra of these two are related. Okay, and you know how to implement this U, right? This is the first thing that you have to figure out, right?
Sorry, can I ask just because?
Yeah.
Questions. One is by spectrum, you mean eigenvalues and eigenvectors, or?
Yes. So what you need is to know how to map the eigenvector from one to the other. Like there is, you can map them, and you know how to map them. And the second is that there is some function where, for example, the singular value of A is some function of the eigenvalue of U, and you know this function.
If that's the case, you really mean something different than what was in Robin's talk, is it? Because in his talk, the relation was, okay, let's plant A as a corner of U. But in that case, there was no relationship at all between the eigenvalues of and eigenvectors of U and those of A, right? Because that's not the relationship it was. The relationship was that, you know, if you project, and etc., right? So you mean something really different from what he meant here.
Actually, the spectra is not. No, I don't think that this is true. Right?
Well, I mean, if you plant a matrix A in the corner of a matrix
Yeah.
U,
Yes. It's not clear that if you do a block encoding that this will be true. To me, the only way I know how to figure out what unitary to put there so that A is in this corner, right, is in a way where the spectra are also, you know what is the relation of the spectra. Like, what Robin was talking is mostly the second step. Like, if you know how this U, if you have an efficient way of putting this A in this corner, for example, okay, then what do? Then you do some way of figuring out the eigenvalues of this unitary, right? And then you go back to the singular values of A, right? This is.
That's not how I understood it, but
Okay, let me not try to explain what Robin was saying, but let me try to explain. Yes. So what I want to say is that, okay, I'm not saying that this is the only way, but the way that I know how to map this A to a unitary U is to basically look at these quantum walks that kind of give you one way of figuring out a U that is related to this matrix A. Okay? If you figure out a way of writing A divided by some factor as the Hadamard product of two matrices, and these matrices have some nice properties, then you can define. You can define a unitary, which is kind of the product of these two reflections, and somehow the spectrum of the singular values of these are related to the eigenvalues of that. Okay, so this was how we got the algorithm. We said, okay, you have this matrix A. I have to figure out a unitary where, if I do basically phase estimation of the unitary, this will basically tell me something about the singular values of the matrix A. Okay, so here is the second step where you don't have to do this phase estimation on U, so you don't need to actually estimate the phase, the eigenvalues of U, but you can do something more clever, which is either this linear combination of unitaries or discretization that you heard a lot, so I don't want to repeat myself. So this way, you're getting this log 1 over epsilon as a factor on your. What you do is that you have this U. Once you have this U, then one thing to do is to do phase estimation on U, right? So this kind of multiplies the cost of applying U by a 1 over epsilon. The fancier thing to do is to actually use this U in a circuit where you only use it log 1 over epsilon and still be able to compute some function of the singular values of A that you want. Okay. All right. And then there is also a third step, which is kind of an amplitude amplification step or a variable time amplitude amplification that kind of gives you another factor in your running time, which has to do with this minimum eigenvalue or singular value of this matrix, which is this kappa, this condition number. Okay? So basically, your running time has these three kind of components. Has the condition number, which basically is the maximum or the minimum singular value of A. You have this mu, and this mu depends on how well you manage to get this decomposition. Okay? And we have different decompositions will give you a different mu. So for example, mu could be the Frobenius norm of the matrix, or could be the maximum L1 norm of a row or of a column of the matrix. Okay? And you have a log 1 over epsilon, which comes from these cubitization techniques, right? So if you need to have these operations up to epsilon, then you have this log or polylog 1 over epsilon overhead. Okay? Okay, so I guess we are kind of okay with this factor here, the log 1 over epsilon, because these kind of techniques were very powerful, the LCU and the cubitization. It's still not clear what is the right parameter to put here. So this is what I wanted to actually say, that we know how to deal with the error, but we know how to deal with the error after you find the unitary that kind of relates with your matrix A. So it's not clear what is the best way of finding this unitary and what this should be, right? So the way we've done it so far is by using some quantum walks that that Andrew and other people have used before, and using a data structure for the QRAM to actually make this unitary implementable and efficient, okay? But there could be better ways of actually doing this. And this will kind of reduce the running time of your linear time solver, your linear system solver, or of any of this linear algebra stuff. Okay? Okay, good. So any questions about this? I just want to make sure that there is a step before you start doing this cubitization thing, which is actually finding this unitary, or finding the way of embedding this matrix A onto the left corner of your thing. And this also plays a role on your running time, right? So to me, the way that I see the cubitization is that once you know how to do that, then you don't have to worry about your errors, because there are very good efficient ways of getting only a log 1 over epsilon in your running time if you want error epsilon, okay?
Can you say again, what's the mathematical question here? If I don't, unrelated to everything else?
Yeah, so one way to see it is that what is the best mu that I can put here so that I can find two matrices P and Q such that the Hadamard product of P and Q give you this A, right? You need some properties of P and Q. You need the rows of P, the L2 norm of the rows of P to be less than 1, and the columns of Q to be less than 1, okay? This basically relates to quantum walks. So we know how to put better things than what I said. We know how to put, for example, the spectral norm of the absolute value of the matrix. But what I need extra, which is why it's not such a clean problem, is that I also need to be able to implement this P and Q in this kind of QRAM model, meaning that I only have one pass over the matrix. I can store somehow the things only with polylog overhead, and then I need to be able to actually implement this unitary, right? For example, I don't know how to do the best walk that we know, because it kind of, you need to know the top eigenvector of the matrix before you actually start doing the walk, but I don't know the top eigenvector of the matrix somehow, right? So I don't know what is the right answer here, right?
So it's more like a data structures question than a math question. You know the minimum.
It's both somehow, right?
The minimum value from U is this thing that you said, right? It's the spectral norm of the absolute.
Yes, but then it's not clear that this is the only way to implement this U. There might be other ways of putting A into the left corner of U that don't have to go through quantum walks. So I agree with you that if you stick with the quantum walks, then we kind of know what the quantum walks do. So then the question is, can I implement the best quantum walk with a data structure? On the other hand, there could be other ways of doing this mapping of the A to the U that kind of don't go through this, right? So that's why it's not clear what you need to do. Okay, good. So now I will start talking about classification because what I really wanted to understand is whether this kind of algorithms will really work on real data. So I needed to find a problem that it's kind of easy to benchmark. So this is kind of classification. And what we did is that we looked at this data set. This data set is basically a bunch of handwritten digits. The question is, can I get a quantum algorithm that has two properties? First, that it will give me good enough accuracy on this. And second, that I can actually say something about the running time, not on the asymptotic, but actually trying to see how it will run on this data. Like, what is the running time? Okay. All right, good. So we had to come up with the simplest classification algorithm we could imagine. Okay. Again, what I assume is that I have a bunch of points in my cluster. Okay. I can have quantum access to these points, like I can create a superposition of these points. Then a new point comes, and what I want to see, I want to actually figure out what is the distance, some sort of distance of my point to this cluster, right? Because what is my classifier? I look at every cluster, I look at my new point, I compute the distances to every cluster, I find the minimum, and I assign my new point to that cluster, right? So this is kind of the supervised classification thing. So what I needed to do is I needed to find a simple way of saying what kind of distance can I compute between a point and a cluster, right? So the simplest thing that we can come up with is this Frobenius distance, which is defined like this. And basically what I wanted to show you is that basically classification kind of comes for free if you know how to create your quantum states, right? So I want to say that if you know how to compute, how to create these quantum states, right? Then classification is nothing more than that somehow, okay? So why is this the case? Well, what you do is that you create this state, which means that on one, you just get a superposition of your points in your cluster, okay? And on 0, you just put your new point x0, okay? So if you know how to...
By cluster, you mean one digit?
No, the cluster is a lot of points that have labeled the same way, like all the 9s, right? So I have all the 9s are points, okay? This set of points corresponds to my cluster, which is labeled 9, okay? So what I'm saying is that if you are able to manipulate these points in this quantum way, like making superpositions of points, then the only thing you have to do is basically create the state, which is basically creating your points. Then you just do a Hadamard on your first qubit, which I presume it's a simple operation to do. And then you just estimate the probability of getting 1, okay? You can repeat it, you can do amplitude amplification if you want, but I don't want because I want something simple. You can repeat this experiment, you estimate what is the probability that you get 1. This is exactly this distance, okay? So basically we defined this distance because this is what we could do, but this doesn't mean that this is a good classification algorithm. So the first thing you have to show is that if you define classification like this, that this actually gives you good results somehow, right? So, and then I guess you do it for every cluster, and then you assign x0 to the closest cluster, right? Okay, so the first remark I want to make is exactly what I said before, is that basically the classification algorithm is not really any harder apart from this extra Hadamard than actually being able to create the states.
Sorry,
yeah.
So the x's, the vectors.
Yes.
So what are the entries? What are the vectors?
So I assume that you have a classical vectors.
So these are real vectors.
These are real vectors. And then what?
So when you say xk minus x0 whole square, so
here, these are the matrices now. I just take the Frobenius distance of the two matrices. So my first matrix are all the points of the cluster. I define this as my xk matrix, right? And my x0 matrix is not a matrix, it's just the same x0 vector many times.
x0
is the new point that you want to classify, right? So I'm saying, look at the matrix that corresponds to your cluster, look at your new point, and look at the Frobenius distance of these two things, okay? Normalized, right? And I'm claiming that, and I'm just saying this is the distance I'm going to compute, okay? It might be a good thing to cluster, it might be a bad thing to cluster somehow, right? But the first thing I wanted to say is that if you know how to create the states, then you do a Hadamard, you measure, and this gives you the distance, okay, the probability. So it's not any more difficult than actually clustering, than actually creating the states, okay? And the second remark is that the accuracy that you get with this clustering is not different than what you would get with like the best kind of classical clustering algorithms like K and N, or like closest K nearest neighbors, or Gaussian classifier, or things like that. Okay? Okay, good. Are we done? No, we're not done, because if you try to classify this data with this classifier, or even with classical classifiers like K nearest neighbor or anything like that, you only get something like 67% of accuracy. Okay? So that's not good, right? And the reason it's not good is that basically this if you just naively take these digits and take them into vectors, then these vectors are not clustered in that space very well, right? So first you have to move these vectors into a different space where they're very good, where they're clustered, and there is where you do your classification, where your clustering algorithm, okay? So this is how classical people also get good classification for this thing. The first thing that they do is not just run their classifier. Yeah?
The record is 95% for K nearest neighbors.
Not before you do preprocessing. So I will show you. Yes, yes. You can get even more. You can get 98, 99% with classical algorithms, but not on the raw data. So all I'm saying here is that if I take this.
It says on Jan LeCun's page there's no preprocessing.
No, I don't. No. Yes. Yeah. So the thing you do, if you want to have a better classification, okay, there are many things you do. You can also do neural networks and stuff. But if you want to do this type of classification, the first thing you have to do is basically take your points and somehow move them into a different space where the clustering is much better. Okay? So this is kind of a classical algorithm to do that, which is called slow feature analysis. Okay? Maybe I don't want to explain, but the reason slow feature analysis is there is trying to explain the following. Like if you're watching a tennis game, these images are very different, and you see many different images one after the other, right? Like this image is not really the same as this image, but somehow your brain can very easily say what this is. This is Federer, playing tennis somehow. So you have two different things. One is that the images that your eye sees are very many and very different, very fast, right? Like if I move like this, everything has moved. But somehow my brain understands what I see, right? So they try to mimic this kind of process, and they say that, look, what we will do is that we will look at these images as a series, and I will look at the derivative of the series, meaning I'm taking the differences between consecutive images. And then what I will try to figure out is what doesn't change in the derivative, right? What is the thing that kind of I keep, so I can see that this is Federer running somehow, right? So if you want to see it from a mathematical point of view, basically what you do is that you look at the derivative matrix. You have to do a PCA on the derivative covariance matrix, and then what you keep is the lowest eigenspectrum, like the K lowest eigenvectors, and these are kind of the features that kind of move the slowest from one line to the other. And this is kind of where you project your vectors, okay? Don't really ask me why it works. I mean,
Don't you have to do alignment to all this?
What is alignment?
So,
What do you mean?
Even if you have two identical lines,
Yes.
but they were slightly shifted.
Yes. You will be terrible if you just try to classify before you do something like that. Yes.
If you're taking the derivative,
Yes.
you're taking some difference.
Yeah.
But that difference will say, well, this thing doesn't look at all like that because it's completely.
Yes, but this is if you look at the derivative. I'm taking the derivative matrix, I'm doing SVD on the derivative matrix, and I'm taking the lowest eigenvector, which is kind of what keeps kind of the thing that hasn't changed between the two.
But just look at this. If you have two lines, you just shift them a little bit.
Yeah. You're thinking of pixels.
You have two
Yes.
copies of that.
Yes.
So you may as well do the SVD on the original picture, and you get the same information because the difference didn't do anything.
So
it was the
That's
alignment
not-
that was the hard part.
it's not that, okay, so they don't call it alignment, but what you have to take into account is the correlations between the pixels as well. So there is another step that I kind of skipped, which is before this, which is you don't look only at pixels, but you only look at pairs or triplets of pixels. And this is the matrix that you actually look at the derivative of. And there things are better because you know that the 9 has to be a circular thing, so you're going to find many things where here there is a white and then there is a black on top and a block below. Okay? So.
What is the, sorry, maybe I missed something. What are the frames? You just get, say, 1 digit to 9 you need to recognize instead of 3?
Yes. So this is 784 pixels, which are black and white somehow. Yeah. So the raw vector is just a vector of 701 bits somehow. And then when you pre-process it, you do many things and it becomes like a vector in some much bigger dimension. Okay? So for example, you also look at pairs, and this is a different dimension and things like that. Okay, yes. So I think one point to get is that if you really want to make something work in practice, it's not easy. It's not just figuring out a theoretical algorithm and say, I'm done, it should work, right? There's a lot of things to be done if you really want to have something work in practice. And I really want to try in the next 2 minutes, 2 minutes, fantastic, to actually show you what we did. Okay, so the first thing we had to do was also come up with a quantum way of doing this part. And this is okay because it's basically, again, linear algebra. We had to do some matrix multiplications, matrix inversions, some projection on the eigenspace, and this kind of we know how to do. Okay? And the important thing here to notice, one cool thing is that if you do a quantum thing like this, what you get, as I said, is not the classical vector projected into the space, but the quantum state that corresponds to this vector, right? But if you look at the classification we did before, I didn't need the classical description of the state. I just needed to have the quantum superposition of these states. So it's fine for me if the output of this is a quantum state and not the classical answer. So I only do this to get a quantum answer out of these linear algebra things. This is good enough for me to do the classification algorithm afterwards. I don't have to do tomography on this thing, get the classical vector, and then classify the classical vectors. Okay? So this is also an important thing. Okay, so the classifier is very simple. I look at my matrix. First I do this QSFA. I project it into some other space, and then I use this quantum states that correspond to this, and I do my classification using the classifier. Okay. What accuracy do I get? Where we got 98.5. Okay, it's kind of the same accuracy they get with classical SFA and k nearest neighbor, for example. Okay. And how did we get this accuracy? Well, this data set has also 10,000 digits which are not labeled, and then you have to run your algorithm on this and see if you get the correct label or not. Okay? So this is how the accuracy comes. Okay, and what is the running time? So here you're gonna scream because this is not very asymptotic, but okay. So classically what you can do is something of the order nd squared. Like n is the number of points that you have. So roughly we have 10 to the 5 points. And d squared, d is the dimension, not the initial dimension of the thing, but the final dimension that you get after you do your pre-processing and then your dimensionality reduction. You get some dimension here, d. Usually d is the one that gives you this, classically is like 10 to the 4. So you have 10 to the 5 points, 10 to the 4 dimension each point. If you have a running time of roughly this, you get something like 10 to the 13. It's like 1 hour on a good computer, okay, to do this classically. So what is the quantum time? Well, the quantum time depends on many things, right? So what we know is that polylogarithmic on n and d, that's very good. So I can stop here and I say I have an exponentially better quantum algorithm, and I can publish a paper. But that's not what I wanted to do. I wanted to really look at everything that goes into the running time and at least figure out what are these things, like for this data set. I'm not going to get the proof that if I change my data, it will work. But at least I want to get some evidence of whether in practice this thing could possibly work, right? So if this doesn't work, then I know that it's not going to work. If this works, then there's some chance that maybe it actually will work. Okay? Yeah?
What type of errors are there in your simulation?
So I'm putting an epsilon error on the singular value estimation, and this kind of carries on the projection as well. And the error, I'm putting a Gaussian around the singular value. Basically.
Algorithmic errors because
yes.
Perfect, but there's also an issue of noise in your simulation.
So I'm doing this on a perfect computer with logical qubits. I don't even know if that works. So I'm not claiming that this works in a noisy computer. I don't even know if it works in a fantastic computer.
So when you say you're including errors
errors, that does not mean noise, it means like the algorithmic errors.
So this is the epsilon that I can assume that my phase estimation can have and still get 98.5 accuracy. I had to take epsilon to be 10 to the minus 7, which means that if I used my previous algorithm, I get the 10 to the 7 running time just from the epsilon. But due to the new very cool algorithms, I only have a log 1 over epsilon, so I'm OK with that. Okay. These theta and delta are the parameters I need for the projection on the eigenvalues. And basically, these are like 10 to the minus 2. Okay? And what I really cared is about this kappa and this mu, because this kappa and mu depend on the matrix. Right? So, okay, so if you put everything together, I get 10 to the 7. So I don't want to keep on that. But I want to show you how these parameters change with the dimension. Okay? So to me, this is the more important. So here, okay, so now you know why I'm not very used in putting diagrams in my talks, so you can't see them very well. But what is this? This is the parameter mu of the matrix. That could be the Frobenius norm, it could be the sparsity, or it could be the L1 norm, okay? And this is how it changes when I increase the number of points. And this is how it changes when I increase the number of dimension. So to me, this kind of shows that if I increase the dimension a little bit more, this thing is not going to blow up. It's not a proof, but you can see how it changes. And also you can see the difference between, if I use the sparsity, I would get a 10 to the 4. If I use the Frobenius norm, I get 250. And if I use the L1 norm, which is the new linear algebra thing that we did for the gradient descent, I get 8, like from the beginning to the end, and kind of similar here. Okay? So I want to show just that you have to really tweak your algorithm to figure out what is the right algorithm to get, but somehow you could safely expect that this parameter here is not going to blow up with the dimension. Okay? And this is the same for the kappa. The kappa is worse than the mu. So here it's okay because it actually drops instead of going when you increase the n. But here kind of, yeah, it kind of plateaus a little bit here. So, yeah.
And what do you think are the prospects for proving like a classical lower bound? Like a poly event or something? You know, is this a query complexity question where you could hope for such a thing, or? No?
So maybe for the recommendation systems, but for this, I don't know what would be the problem. But I can come up with. Okay, I can come up with. Okay, so basically, what I wanted to show is that there is some hope, and maybe you can claim that there is some evidence that quantum classification algorithms can handle bigger dimension. And to me, this is the important. I don't care about a faster algorithm. I get the algorithm that can get better accuracy running 1 hour on a HPC machine, which means that I can increase the dimension of the points, hence I will get more accurate, and the running time is not going to kill me because it doesn't scale as badly with this dimension as the classical one, which is cubic on the dimension. Okay? Why? Because this polylog on the dimension is polylog, and these guys, for this particular thing, they don't really blow up. Yeah.
Got a bit of a question with this. There isn't necessarily a single classical analog for many of these methods. One of the things, so I was kind of wondering, what would you expect the comparison between this would be if you were to take a look at stochastic methods for figuring out the difference? Because those don't necessarily depend on
yeah. So you mean on the running time or on the accuracy?
Well, actually, ultimately, there's going to be a different trade-off for both of them.
Yes. So what we looked at algorithms that kind of at least can get you 98, 99. There are algorithms that can get you 99.5 using neural networks and stuff. I don't know how to do anything on that side. Okay. So we looked at the algorithms that kind of do some dimensionality reduction and then kind of classification. Okay. These algorithms give you around. They can start from 95 up to 98.78, okay? And the running time of these, so what I know is that the classical paper that does classical SFA plus K and N, right? It did exactly the same dimension as us, dimension 35 with polynomial expansion of 3, and it takes 1 hour on the same machine.
I guess all I'm saying is that formally, you can get.
It's not. Yes.
KNN using
yes.
stochastically estimated distances.
Yes. Yes. The problem is not the KNN. Like it's not on the classification that is your problem. It's on the dimensionality reduction. Your time bottleneck is not the classification. So what you need is better algorithms for PCA, basically. And we kind of use the better ones that we found around, like from the classical machine learning toolkits, basically. It could be that there exist better, I mean.
Thank you.
Yeah, of course. But I'm saying we used the classical standard library for doing the SFA, right? Which hopefully, asymptotically, it's ND square. You cannot get, and we used one that people use. And for the K and N, it doesn't matter. It's not where you get the 10 to the 13 somehow. Okay? All right. So I get over the K-means. Summary, can I say one thing? Or? Okay, one thing. So, okay, I want to say, why do I think that maybe quantum computers could do good stuff for optimization in machine learning? Okay, and it's not because I managed to prove something or other people proved something, but to me there are two things. First of all is that it's not a worst case thing. Like you have these matrices, you need to do some linear algebra on these matrices. You're not trying to see what is the worst case scenario that will happen with your matrices, right? And usually these matrices have some structure, in the sense that it's not, maybe the structure is not obvious when you look at it, like when you look at the pixels, but what you do in machine learning is that you figure out how to map this thing into a space where there is some structure. Like if you want to cluster, it better be that your data is clusterable. If it's not, then there's nothing you can do. If you just get uniform points in the space, no matter how you cluster, it's not going to be a very good cluster somehow, right? You want to be able to cluster when your data can be clustered, right? Data that can be clustered is low rank, for example. Right? If you have 10 clusters, it means you can come up with a low rank approximation of roughly 10 that can actually. So what I'm saying is that there is a lot of, you're trying to get something out of your data, some structure that exists. And many times the structure kind of translates to things that you can use to have good quantum algorithms, for example, good low rank approximations. And the second, and I really finish, is that these algorithms are very robust to errors. You have this log 1 over epsilon kind of dependence on the error. And second of all, ML is not an exact science. You don't really want to find an exact solution. You want to go close to a solution. When you're doing gradient descent, I don't care if I really go to the best way I can go there. I can go a little bit to the left, a little bit to the right. I'm still going to go close to my local minimum after a few steps, right? Okay, so that's it. Sorry, I'm done.
I guess we're way over time, so.
Yeah, sorry, yeah.
Questions? No, please.
So, I think the best classical approach to the handwritten digits problem are convolutional networks.
Yes.
And you said you are extracting features from the pictures.
Mm-hmm.
So are you doing something like a convolution here or not at all? As a pre-processing step.
So the pre-processing, what I do as the pre-processing is exactly what the classical people were doing when they were using this method, which is you do a PCA in the beginning, then you do a polynomial expansion to get the correlations between the pixels, and then you look at the derivatives and take the smaller ones. I don't know exactly how the neural networks work. But you're right that if you want to go to 99.5 accuracy, then the ways that people do it is by neural networks. And I don't know how to do quantum neural networks. I also don't think that we know as a community how to do quantum neural networks, but that's a different.
Would it be possible to simulate your quantum algorithm with a little bit of depolarizing noise on all the qubits, kind of simulate near-term computation? So see whether it still works in that case?
Well, the problem is that the best thing you can simulate is like 40 qubits or 70 if you know, something between 40 and 70 maybe.
Your number of qubits is logarithmic in the dimension.
Yes, so you would need to really write it down, but my dimension is 10 to the 4, 10 to the 4 is 2 to the something. It could be, I don't know, it could be. Yes. What we did in the simulation is that we simulated the classical linear algebra that the algorithm does, including the errors of the quantum procedure on perfect qubits.
Okay. Do you want some? Just one.
Yeah, I'll make it an awesome.
Just thank.